So I'm going to be talking about our activities in ion atom hybrid systems over the past years, and that will be linked to formation of charged molecules. Now, not from that much from the microscopic side as you got it via detailed studies of electronic structure calculations and collisional things, but more on the side of modeling it from scratch and then doing the bridge between few to many body systems. Up front, this is theory, of course, and the work has been done by Johannes Schurer and Antonio, who is in the audience heavily, and also Dan, who has had also a poster and is, of course, also in the audience, and you can chat with those. Also, if you feel you have some extra questions. And all of that has been funded by a fantastic funding instrument and excellence cluster, the Hamburg Center for Ultrafast Imaging, which is greatly appreciated from the German Science Foundation. So what I'm going to be talking about, very brief motivation, we have heard a lot, so we have one slide, that's it. And then we go into our specific setup, how we model it, and one slide with the computational method. And then there's two main sections, which are kind of bit of history in the sense of it's not the most recent work. So the capture dynamics of an impurity ion, what happens if I suddenly create an ion out of a system and what's the follow-up, non-equilibrium quantum dynamics. And then the structure of mesoscopic molecular ions, which is a stationary state picture, phase diagram. And then the more recent things, the ongoing project. So I will quickly flash what is currently ongoing and without showing a lot of results, just to give you an update on what's up in the group. So motivation, well, we have heard a lot of excellent work on what you can do with atom ion systems, controlled state-dependent atom ion scattering. Getting more and more into the details, understanding more and more of channel-dependent scattering properties, elastic, inelastic, and the one of the beautiful processes which have been described, chemical reaction, charge transport. Of course, there's also ways of using ions in order to control tunneling and state-dependent transport process, now going a little off from these precise quantum chemistry-based calculations. And going into type of quantum simulation model systems. Spin-dependent interactions are very important. And then there's this original suggestion that you bring in phonons into the system by having ions. So that's what you do not have usually in standard conservative optical lattices and neutral species. So that adds a real quality. So you can have charge phonon coupling and things. Historically, also mesoscopic molecular ion formation was a big startup for the, and then more recently, of course, this beautiful work on atom ion Feshbach resonances, which now adds a toolbox, an additional tool to the systems, which will be greatly appreciated and can be used in the future. So, what is our atom ion setup and our computational method? Well, we have that scale in the system, the extra scale connected with R star, connected to the polarization potential, 1 over R to the 4. And then we start modeling for our few to many body systems, the ultracold atom ion collisions. And one thing here is you change the quantum defect parameters and you have a strong variability of the scattering lengths. That's something which you wish to have. And you get that also in particular from the model potential, which I'm going to show you here. So that's what we're using for our elastic collisions between, say, the ion and the bosons, which are forming the complete system. So that has a long-range tail, it has a 1 over Z to the 4 polarization tail with a kind of a cut-off here, and then a repulsive part, which is a Gaussian, with a positive V naught, of course, that kind of makes up for the regularization towards the Z equal to 0 position. So we reproduce correctly the long-range tail, the 1 over Z to the 4. We regularize at the origin the divergence. And with that, the parameters which are in here, we kind of tune the system. And this is one picture shown here, which shows these different potentials for different omega values. And which just, this is the 1 over R to the 1 over Z to the 4. This is all 1D. Sorry, forgot to mention. This is all 1D simulations. And then we have this potential, so you can, with varying omega, tune the different behavior of the potential and tune the amplitude at z equal to 0 with the V naught and with the gamma equally. So here, as a function of gamma, is shown this, and omega is shown what these even and odd quantum defects are, and you see that there's quite a bit of variability. There is a bit of an independent variability of the even-odd part. Here there's little sensitivity with respect to gamma, and there's a lot sensitivity with respect to omega, such that moving with omega and gamma in this two-dimensional landscape, you can really vary the even and odd quantum defects almost independently. Now, a second tool which we are using, or second preparatory measure, is, of course, we are doing dynamics. So the method we are using is, so to speak, the Bose course, which has been built in the group, roughly going back to 2013, and then in a second stage of developments in 2017. As you can see here, this is the ML-MCTDHB method. That's multi-layer, multi-configuration, time-dependent Hartree for something, meaning for bosons, for mixtures of bosons, and fermions, or fermions, and particularly also having this case of ions and ion neutral hybrid system. So this is based on the variation principle. You start top-down variation principle, and you make a multi-configuration ansatz. You have different layers which are sketched over here. So the method is based on a hierarchy of different layers, where on the different layers, the different degrees of freedom are coupled together. That's the essence of it. And then you have these top layer, species layer, particle layer, where you couple all of that together. That's the total wave function. That's the species decomposition. That's the individual species many particle configurations. That's the single particle function decomposed finally on a grid described by DVRs, discrete variable representations. Now, the key thing about this method, why it is so efficient, is kind of sketched over here. What you do is, along with time, you time evolve your single particle orbitals. So your single particle orbitals are not God-given static, but they are time evolving. And therefore, you kind of automatically seeking the corner and Hilbert space, which is the one which is optimal for describing your system. And that adds very much to the performance of the system. Yeah. Technically, this is just a set of coupled nonlinear partial integral differential equations, so there's a bit of math in this. So anyway, we don't need to go into more details here. That's what we're going to be using. So let's look into one case, namely, we look into the capture dynamics of an impurity ion. So what do? We have harmonic traps, yeah? And in these harmonic traps, you suddenly create an ion, and you assume this is fixed position. You don't give, at this place, a dynamical degree of freedom to the ion, but you have all the bosons around it, in this case, simulations 5 to 20 or more bosons, and you're interested in what happens dynamically after suddenly creating the ion. So you have this combined trap. That's the trap up here, the Z squared behavior, and then this inner part is, of course, dominated by the atom-ion interaction potential. So that's the all-together, so to speak, single particle potential which you have. And then you have these levels. So in there you have two bound states. The system is tuned. You have an even and odd bound state, which is an atom-ion bound states to be addressed. And then there's gradually, with increasing excitation, you have kind of trap states, which pair also in even and odd. So now this is what is happening, actually. So you see, at time t equal to 0, suddenly the ion is created. What you see is that there's different time scales in this system. First of all, you create a bunch of bosons in here, which is a kind of sudden implosion of the bosonic cloud into the bound states, yeah, but this part is not static, but it is oscillating, as you can see over here. So it's kind of an ion-bound breathing type oscillation which happens, and you see also from the time-dependent energies, and these different curves are the energies. There is an oscillation here of the potential energy, which is kind of smooth, but then there is with different frequency, an oscillation of the ion-bound part, which oscillates according to this oscillation here, and then some part where you have a highly irregular type of fast oscillation, which comes from the part which is here at time t equal to 0 emitted into the trap, and then coming back here and crashing into the cloud, into the ion. So that is responsible for these heavy oscillations here of the atom ion energy part. Yeah. So, and then you can use this up. This is the complementary part, of course, to add up to the total energy. So what you have, a periodic emission and back reflection of atoms into trap. You have a density fraction in ionic bound state oscillations. And that is a major features of the dynamics which happens. So if you look into the longer time, if you go back for a second, you know, this is units of h bar over E star, 10. Now, if you come here, this is much longer time evolutions here. You see also that things are repeating, but then you also see that things get fanned out, and that there's a disappearance and recurrence of the ionic oscillations. Here it's more pronounced again. At the beginning it's very pronounced, but here is much more faint. So you have revival structures over time, which are also documented here by the single particle density matrix picture, which becomes more longer range coherent, and then these die out of the off diagonals here, and then the revival of the off diagonals here. The contrast is not very good here, I apologize for this, but that essentially shows the loss and regain of spatial coherence between inner and outer density fractions in the system. You can do analysis of this in terms of cluster, coupled clusters. So you do a decomposition of the whole system in the spirit of BBGKY, where you have a hierarchy of density matrix. Here it's a hierarchy of singlets, doublets, triplets, which are coupled to each other, and that you can compare to the exact simulations. Now, what do you compare with? Well, we look into the fidelity, which is the overlap, or it's essentially the expectation value of the time evolution operator. So, or the overlap of psi total wave function at 0 and psi at t. And then you do the Fourier transform, which is shown over here, and you look into this spectral analysis, and you see one main peak, yeah? That's dominant peak. That dominant peak is this ionic oscillation, which I have been showing you, the inner part, which is breathing, yeah? And then you see a series, a progression of other peaks, which are almost equidistant. And if you classify those in the cluster expansion, what you see is that there's these blue open circles, the P17, P19, these are singlet excitations into the trap. Yeah? And these singlet excitations, if you calculate them, they pretty much match with these peaks, which are the Fourier transform of the exact simulation. But then there's another part in here, this low frequency peak, that is not coming only from the singlets, that's coming from the doublets and the coupling of the singlets with the doublets. And so it's a mode which needs both and is of correlation origin. Yeah. And here you see how this changes with particle number, and you see the behavior, the one, again, comparing the non-interacting part with the interacting part, and you see that there's a decrease of the frequencies with increasing particle number. Okay, so so far dynamics, there's lots of other beautiful things you can do in the course of dynamics. This was just one example, what you can do, and actually Dan is currently pursuing a number of other things in terms of non-equilibrium dynamics. So, but let me talk for the next few minutes about the structure of mesoscopic molecular ions, which goes back to a work in 2017. So what is that? Well, we have seen we have bound states. We have these lowest, the highest bound state, the even and odd. And of course, if you have bosons, you can put in there bosons in the sense of forming a charged molecule. And now we include the motion of the ion. Yeah? Previously, it was just fixed, no dynamics for the ion itself. For the rest, yes, but for the ion. Now we include the motion of the ion, and we look into many-body bound states. And what are, just to give you upfront the results, what are the main observations? Well, you can form a massive quantum object by just putting the bosons in there, making these effectively as a bound state heavier and heavier. And you can have a phase diagram of such a compound system. I will show it you in a minute. You develop a type of a shell structure. You can look then into the dynamical response in the spirit of also what Georg has been showing of a polaronic structure. And so you can look at the dynamic response of these quasiparticles, so to speak. You can look into what happens if there is no more bosons possible to kind of put into these bound states. Depending on interaction strength, you get a self-localization of the ion. You will see that. So that's the route. You can form such a molecule with a finite number of particles at a given intra-bosonic interaction strength. You can kind of ionize or dissociate, whatever you want to call it. Then you can have the molecule, which is surrounded by additional bosons, so something like a molecule under pressure. Yeah. So, and that's the phase diagram. So what we have here is, as a function of the particle number and as a function of the interaction strength, the kind of phase which we have, with one dividing line, the number of critical bosons in the system. Now, for mu less than zero, mu less than zero means you add particles and you still have a negative energy difference. That means you sort the particles into the bound state. Yeah. So in that sense, this is all building up with increasing particle number, heavier and heavier, or maybe larger and larger of these ionically bound molecules. Now, if you cross the boundary here, you're not capable anymore of feeding in particles into this mesoscopic object. But what happens is that you put this into a surrounding sea, so to speak, pictorially speaking. And the border between these two kind of, the crossover, the borderline between these two phases is this critical number you can feed in order to form the molecule. Yeah. So, mesoscopic charged molecule, unbound, trapped atomic fraction, and so forth. So this critical line can be obtained roughly via some simple energetical considerations. Now, if you want to describe this, there is several kind of ansatz which give you insights into the system. The one is, of course, the most primitive is the mean field. That's not giving you what you should get, telling you up front. If you go into what is the gross ansatz in the ion frame, where you take the ion as a coordinate and the relative coordinates of the bosons with respect to the ion, which induces already correlations into the system, then you get something which is already kind of giving you a bit of correlation of the system. And then, of course, you can compare with the method I mentioned before, the ML-MCTDHB, and you can do relaxation, which means imaginary time propagation, to get the ground state. Yeah? Instead of propagating in real time, imaginary time, you do it a little smarter. You have so-called improved relaxation, but that's more of a detail. And you can get then finally the dependence of the ground state energy and properties, since you have the complete wave function properties as a function of whatever parameter you want. Now, this is here giving you the energy as a function of a particle number. As you see, it's going from 1 to 20. And you see a mean field is quite off. Gross ansatz is much better. The correct or the kind of converged result for including all correlations is the full curve. So, which is even lower, of course. Now, what is happening actually? Yeah? So this is pictures of the density of the atoms, the bosons, and the density of the ion. And this is for 5 particles, G equal to 3, and you see, okay, that is pretty much similar type shaped. Yeah. Now you increase the particle number, yeah, going from this comparatively low number to a higher number, and you still and what you see is that this ion, you feed the atoms, the bosons, into the bound state, and you localize your ion much more than it was here, yeah. So because it becomes a massive object, it localizes, and then you see also at the same time, due to the localization, now you see in the single particle density that the atomic density has 2 wings, yeah, and which is because of the atom-ion interaction type, core, repulsive core plus individual in 1 dimension potential wells, yeah. And then if you go from G equal to 0, non-interacting bosons, to G equal to 3, quite strongly interacting bosons, you see that you develop a tail out there, okay? Now that tail is duly because of what I mentioned previously. You're not allowed with these interaction strengths to put all the bosons and condense them into the ion bound states, but you have to spread them also out in the trap, yeah? You can sort in only a limited number of bosons due to the repulsive interaction in the bound state. And this, at the same time with the localization, of course, with the ion becomes now massive, leads to this formation of this density profile here. And you have the wings, and these wings are, of course, from the bosons in the trap. Yeah? And, of course, you can then also look into other quantities, like over here showing the distance, the average of the distance and the distance distribution between atom ion. And what you see is also here, you have a peak at short distances, which is the atom ion bound effect. And then you have a tail, which develops over here, which is responsible, or corresponds to that tail over here, which you develop actually. So now you can also look into the population of bound states, and because we have two, we have an even and an odd state, and this is actually shown over here as a function of the particle number, how much they are populated. So you see that also at the very beginning, you populate both, not only the even state, but also the odd state. So and that stabilizes actually the molecule, yeah, because you have two states available in your bound state scenario. And this picture just shows you again how you kind of localize the center of mass with increasing mass of the atom ion hybrid bound state, and that then shows up finally in the picture I've shown you for the densities. Now this is the self-localization effect, which I've been already pronouncing. So it is the variance of the ions and the atoms as a function of particle number. As I told you, mean field is pretty much off. You know, that's the curve down here. It doesn't give you any of the features. If you go to the G equal to 0 case, which are the crosses, you have a monotonous decrease with increasing particle number of the variance, which simply comes since it's becoming a massive object. It localizes more and more, variance gets smaller and smaller. Now, if you do the same thing at G equal to 3, where you have the repulsive interaction among the bosons, then you have a curve which has a minimum and goes up, yeah? Which has a minimum and goes up, yeah? And this holds for both the atomic and for the ionic variances. And this is the fact which I mentioned. You can feed into the ion bound states a certain number of bosons, but then they go to the trap such that you spread more again after the minimum, which makes then you to the so-called molecule under pressure. So this is we have only 2 minutes left. So maybe we just skip this one to stay in time. More recently, because this is already, you have seen this work from 2017 and so, more recently, Dan has been working in quite some detail on the three-body system in the atom ion system, and you can talk to him or to me, whatever you wish, to get more details on this. But for the remaining 2 minutes, I would like to say a few words about the currently ongoing projects. There is this beautiful work which has been presented from Johannes' group and Tillmann's group from the theory side with ongoing experiments and from the already done experiments on this beautiful new bound state of an ion to a Rydberg atom. Yeah? With a flipping dipole and all this beautiful physics and which happens around this avoided crossing. To make a long story short, what we're currently looking into, and all of that is just here, done here and reported on here. So this is the remark which goes back. We're currently looking into ultra long range molecules, which we have a different binding mechanism, which have been history on their own, just beautiful physics. Tillmann has done a lot with that. And and now can an ion bind to such an ultra long range molecule? That's what we are currently looking into. And tentative statement is yes. So another project which is currently ongoing, and Tillmann has been indicating that, we are collaborating with the experimental group, and there's this fan, you know, with the ion microscope, where you have that 129S state, and then it goes through all these crossings with the degenerate manifold, the hydrogenic manifold from 126, and So if you think about not inspecting these avoided crossings like the one here, yeah, and thinking about vibrational bound states, now the question is a completely different one. Now the question is, if you initialize here an ensemble, and then it propagates, and we can monitor that, and experimentalists can image that, then you're having here a huge number of avoided crossings, and there we are looking here into the dynamics and are interested in how does that reflect itself in the distribution of the ions, and that is shown over here. Comparison, just a brief glance, the dynamics, how it changes over time when you sample that and experimentally, and when you describe it theoretically in terms of Landau-Zener, semi-classical approach, Landau-Zener plus classical trajectory calculations. So there's quite a bit of a good agreement over here. Yeah? And last but not least, there was also the poster by Dan, and that's a project where we are looking into, you take an ion and you drag it through a BEC. In this case, this is non-interacting because we don't want to create solitons or whatsoever. And you pose the question of what can you achieve in terms of controlled state preparation. Yeah? You want to have a final target state once your ion has passed the BEC, and you want to optimize that such that you put your, for example, your bosons all into a given certain level, and you steer through this mass of avoided crossings according to an optimized pulse, which you design and want to get finally the best fidelity up to a certain given state. Yeah. So that's another way of using ions, and using only impurities here makes a difference. Yeah. So the extra scale, which is in here, R star, really helps you for the state preparation. Yeah. I'm going to leave you with that since I'm already over time and I have a red flashing light, and I don't want the chairman to become upset. Thank you so much for listening.
Great, thank you very much. Questions? Olivier?
Yeah, thank you, Peter. Just to be sure that I understood well, everything that you reported are indeed 1D simulation, right?
Absolutely.
So we have to see the system as some kind of a chain of atoms, and then you have mode this way. Right. I'm asking because at some moment we are seeing that ions surrounded by atoms.
Right.
Okay, you had this picture during, but your surrounding means on the line, right?
On the line.
Okay.
On the line.
And those projects that you were reporting at the end are also made in the same framework of this 1D simulation?
Well, these are different setups. This is 1D, yes, correct. Yeah. This is what it is because it's the radial collision, so it's the physics of the system. And the other one is again also ultra long range molecules. So there's nothing to do with this 1D modeling. Okay, it's the full full system.
Thank you.
You're welcome.
When you work for the for the mesoscopic ensembles, for the mesoscopic bound states, so you have interactions between the bosons,
right?
Yeah, and I think G was positive, so there are, in principle, there should be molecular bound states of the bosons available, but you take them into account in the sense that they are available in your model to be populated.
No, there's no boson bound state.
Why not?
We have repulsive interactions, repulsive contact interactions in 1D.
In 1D, yeah. Okay. So that's a dimensional, okay. So that's really different than in 3D, of course.
Yes.
Yeah.
Yes. Okay, the regularized pseudopotential in 3D would have bound states. The repulsive G regularized pseudopotential in 3D would have bound state.
Yeah. So still, can you artificially create a bound state and see what would happen? Yeah.
So you want to have the combined system. The atom ion could have this, what I showed, and there could be also kind of molecular formation among the bosons. Yeah. That's would be your wish.
So there's a little bit of a competition, which bounds states.
I mean, it becomes a little harder for the methodology, but it's possible. I meant to say that is easier than if you would have suggested for us to include the transversal dimensions. Because that's, I would say, still feasible, but it becomes an CPU time-wise a really massive thing.
Okay, thanks. Yeah.
You're welcome.
Great. Well, any other questions? We're running out of time. Great. Thank you very much.